I mean, close your my mic on. So this goes there. Hello. That's not the Why is Teams open in the background? Because it's open on Teams. I see. You should be like going anyway. Because you have speed, that speed is really? Yeah. Really bad. Huh? Yeah, okay, cool. You good? Is this camera on too? Oh wow. I feel so cool. All right, we're gonna get started. Welcome to the Drivetrain new member lecture. I'm Matt. I'm the Drivetrain lead this season. I know I saw some of you at the GBM, so good to see you again. All right. So what is Drivetrain? Drivetrain, like it says up there, it's basically everything from the output of the engine to the driven wheel. So it's a rear-wheel drive car. So we have the engine mounted in the back. You can see that front sprocket there is what mounts to the transmission essentially of the engine. So we've got the front and rear sprockets, the chain that connects them, the differential itself, the differential mounts, and then the CV joints and the half shafts. By the way, interrupt me at any point or raise your hand if you have a question about anything. Don't mind stopping. So for this year, how is Drivetrain changing? And if you went to the PER, yeah. I'm sorry, I know you just said it. Would you go back and explain the CV joints? Yeah, so I'll get into those later. I've got like diagrams and stuff. So yeah, same thing with this slide. If there's anything on here that doesn't make sense, I'm going to go into more detail. So, but yeah, so basically we're changing the final drive ratio. That's a big thing to hopefully improve our torque out of starter corners. We can achieve this by changing sprocket sizes. There's some validation stuff, which I'll show later. We're also changing the differential, so that's probably the biggest change for this season. We've been running a Torsen LSD for a while with a custom housing that was made in shop, and we're switching to like an off-the-shelf clutch pack LSD that's basically built for FSAE. So a lot of the other teams run it too. Pretty much all the other teams run the same differential. So yeah, basically the Drexler is a lot more tunable, and again, we'll go into that more. And then lastly, pretty much every system is trying to decrease weight every season. For Drivetrain, there's not a ton of room for weight savings because at this point, a lot of stuff is off the shelf. The differential, the half shafts, the stub shafts, the joints and everything. Chain, you can't really change. The sprocket at this point is pretty much as light as it can be. So it's really just the rear sprocket, and then the differential mounts are really all we can really try to change to save weight. But the Drexler is about half a pound lighter than the other diff, so we will be saving some weight there. So yeah, on the top, that's the old diff. Obviously, it's not see-through like that in real life, but that's the cab. And then below it is the new diff. So yeah, that's the Drexler. It's all gold and shiny. It's very exciting. So I wanted to go over like the fundamentals of the differential because it can be a pretty confusing topic for a lot of people. Even I sometimes kind of get confused as to how it works. So basically, it's an open differential design. So this part right here, that's essentially what an open differential would look like. So that's what a lot of like economy cars and stuff like that are going to have. And essentially lets your two wheels spin at two different speeds. So if imagine you're going around a corner, this might be obvious to a lot of you, but imagine you're going around a corner and that's your inside wheel. That's your outside wheel. Wow, it's terrible. Obviously, your outside wheel is going to have to take a longer path than the inside wheel. So it needs to have more rotations than the other one. So basically the differential, at least an open differential, allows you to do that really easily. So the downside is if one of your wheels starts to slip or say like came off the ground completely, the torque from the engine to the wheels, it's essentially going to take the path of least resistance. So if instead of giving power to the wheel that's still on the ground, which is what you would want, it's going to start giving all the power to the wheel that's not touching the ground, which is not what you would want. So that's the major downside of an open differential, and that's why they're not really used in racing at all. On the other hand, you have, like on the other extreme, you have a spool differential, which if you heard about people like welding diffs for drifting and stuff, that's essentially what that is. It's just usually a little more classy. It's just a solid connection. And the benefits of that is that it always splits the torque between the two wheels evenly. So if one wheel comes off the ground, you're still going to be getting power to the other wheel. But the downside, of course, is that when you're going around a corner, your wheels can't turn at different speeds. So sometimes you end up with like scrub or skip like within the wheels as they try to sort of catch up to each other, if that makes sense. So with an LSD, which stands for limited slip differential, you're kind of in between those two. And then we're able to tune and kind of shift more one way or the other. So open differential, really good for turning. A spool differential where they're connected, really good for like straight line acceleration and stuff like that. So yeah, and let's talk about the clutch back one that we're going to be using. So like I said, it's an open differential with the addition of ramps and clutch back. So everything right here is what's all exploded out there. So all that stuff is fit into this tiny little area. You've got, so it's saying during acceleration, the spider axle, which is this black sort of cross here, is forced into the ramps of the pressure rings, which pushes them outwards and compresses the clutch back. So these two halves are these two pieces right there. Okay, so they're separate, right? And where they connect, it forms kind of like an oblong square, if that makes sense. And you have sort of ramped angles here. So when I'm saying ramps, that's what I'm talking about. And if you guys have taken statics already, which a lot of you probably haven't, maybe some of you, okay. It makes sense either way. If you push this down or up, you're gonna have some of the force going this way and some of the force going that way, right? So depending on that angle of the ramp, it determines how much of the force is sent to the left and right, which is what actually compresses those clutch packs. So, so it's kind of hard for this to make sense for some people, but these rings here, which are called the clutch plates, you can see how they're kind of toothed on the edges. So those are actually mated with the housing of the diff. And then other ones, which are called like friction discs, those have the teeth on the inside, okay? And those are mated to these gears here. So those are actually mated to the wheels essentially. So those rings are usually spinning out of phase, if that makes sense. So when they get compressed, it essentially locks the diff together and treats it like that spool diff that we were talking about. So it's based on acceleration and deceleration, whether or not it starts to lock. So that's kind of what is explained there in those other points. The pressure increases the friction in the system and increasingly binds the wheels together. And the Drexler is a 1.5 way differential, which means it locks on acceleration and deceleration. So a one-way differential looks like this where the ramps are. So it would only lock in acceleration, and then in deceleration, all that force would be going that way and none of it to the side. And then a two-way differential is where those angles will be the same. 1.5 way just means that it locks in both, but less on deceleration. That's kind of what you see there. You've got like 40 degrees on the one side and then 50 on the other. Any questions about this slide? I know I went over a lot. Yeah.
So what makes like this differential adjustable? Like you add like clutch plates or?
Yeah, so that's actually the next slide. But any other questions about this slide before I move on?
Cool. Jake, can you move like
yes, adjustability. So it has presets for those ramp angles that we were talking about. So if you take the diff apart and you change which holes that spider axle is going into, you have 3 options, and it changes those angles. So it's showing you both the XL and the decel ramp angles on there. So it just kind of determines how much of that force goes to the left and right into the clutch packs. Shallower the ramp angle, the more aggressive the locking factor. It also determines what's called your torque bias ratio. You guys might have heard that term before. It's a little more like wavy when it comes to the like a clutch pack LC because it doesn't necessarily like lock. It's not like not locked or locked. It can kind of be in between. So your torque bias ratio is a little harder to sort of put into a number. So yeah, and we're going to be able to tune this based on either driver feedback. So if the driver's saying, every time I come into a corner and I'm slowing down, the car is kicking out, which might mean that it's locking too much on decel. So we might change that by changing the ramps, or we're also able to adjust the preload in the clutch packs. So basically just how tight those packs are to start with. So it sets a baseline degree of locking. So you would need less force from those two side plates to actually get the diff to start locking because they'll already be sort of spinning together. So yeah, and then the torque difference in the wheels would have to overcome that resistance to be able to rotate at different speeds. So like I was saying before, it's just all a trade-off between open differential and completely locked differential. So having a better, having higher preload and a higher degree of baseline locking means it's going to lock up more, which is good for, again, like accelerating or decelerating, because it kind of gives you stability in the wheels. But it makes it harder for them to rotate at different speeds. So the car will be more understeery in a corner. I don't know if you guys are familiar with understeer and oversteer, but yeah, it'll feel like the driver's trying to turn and the car's not wanting to turn as much because the wheels are having trouble going different speeds. So yeah, any questions on any of this slide? No? Cool. And then the last thing is the clutch packs. There's really not a ton of adjustability in this, but what you can do is instead of having them alternate like that, you can have the two friction discs next to each other and then the two clutch plates next to each other. And that is basically going to cut your, I don't know if it's actually cutting it in half, but it would like significantly decrease how much it locks. So that's probably not something that we'll ever do, but it is just another option. So yeah, the next thing is the diff mounts. So here's some of the CAD for the Drexler so far. And the two diff mounts are on the left and right there. So the goal is to keep the center line of the differential as forward as possible, close to the frame. So you can kind of see there that that dimension right there and there is very small. So we're trying to push these bearings as close forward as we can, because you see it in any of the other slides, maybe in the first picture. So the diff is pushed back from the center line of the wheels. So we're trying to minimize the angle of the half shafts and the CV joints on the diff. And again, we'll talk about the CV joints in a minute, but that's the main goal is we're trying to minimize that angle because they're more likely to kind of fall apart at a higher angle. So yeah, and then if you look at this picture, you can see the sprocket is on the left, and then you have both of the mounts on the right. The current car has the sprocket in between the two. So as far as like statics goes, it's actually better what we have now, because like you can see here, the sprocket is going to exert a certain amount of force on the chain, which will exert on the rear sprocket onto the diff. So you're going to see, essentially, that's the highest load that we'll ever see, and that's seen at launch. So when we're trying to do a really hard acceleration. And then just using statics, you can kind of see you end up with a really small force on the right mount, which you can see over there. And it's actually going to be negative because it's like a seesaw, right? So you've got a reaction force from the left mount there, and that's actually going to have to balance out both the sprocket force and the force from the right mount. So if you see all the way on the right there where it says left mount force, you'll end up with a force higher than what's actually seen from the engine. So I don't know if you guys followed all that, but yeah, basically really high load on the left mount. That's why it's kind of comically bigger than the right mount, but that's just kind of how it has to be. So we actually have stacked bearings in the left one. Yeah, you can probably see that. So yeah, there's two of the same bearing next to each other on there. You guys, unless you've taken Mech 1, you probably won't recognize any of this stuff, but basically we have to, just like with every other design choice on the car, you want to make sure that nothing's going to break. So we just have to validate that the bearings that we're going to pick are going to withstand everything that they're going to see in the season. So I basically found an average wheel speed for an endurance run, and I came up with just an arbitrary number of hours that I think the car would have to run for a season. And then we're able to use, it's called a C10 bearing life calculation. And it basically says, okay, this is what the left and right mount are going to have to be able to withstand. And then on the far right there is from the actual bearing manufacturer. So yeah, that's just like validation stuff. Any questions on anything right now? Cool. Okay, so yeah, lastly, or not last, we got a couple more things, but front and rear sprocket and final drive ratio. So final drive ratio is just the number of teeth on the rear sprocket divided by the number of teeth on the front sprocket. Okay. So we use a lap simulation tool. So it's a MATLAB program, and we're able to put in an actual track. So we're using the track from last year's endurance, not last year, last season endurance. It basically makes straight lines, and then you call those, I don't know, straight lines and basically parts of circles, and it simulates what the actual track is. And then we're able to basically run a bunch of scenarios, and it spits out, okay, based on the FDR that you pick there, it'll give you a simulated amount of points for endurance. So you can see it kind of peaks around 2, but it really doesn't drop off that much to the right. So this kind of gives us a range of FDRs that would be ideal. But just like with everything else, you want to try to connect it to something, in the real world. So last season, we ran essentially a 2 FDR. So it was 15 tooth front, 31 tooth rear. You divide 31 by 15, you get 2.07, something, right? So if you look at the data from endurance, which is this graph right here, this is just wheel speed essentially. You can see that where it dips down here, that's where we're slowing down to turn in a corner. And you can see we're exiting a lot of these slower corners at around 20 miles an hour. So the problem is if you look at the tractive effort plot, so you can kind of think of this as the torque curve if that's easier. But essentially at 20 miles an hour here, we're basically entering a big dip in our tractive effort plot. So what we saw was a lot of times when we were coming out of corners during endurance, the car was like bogging down. So that's not good, right? But the FDR was good for acceleration. So the plot on the top there shows each gear's tractive effort. The one on the bottom is just a combined one. And those little circles are essentially where we'd want to shift. And then the yellow line is our tractive limit. So if we put more torque than that tractive limit, the wheels wouldn't be able to stay connected with the ground. So being above that limit isn't really helpful. So that's what that graph is. But yeah, if you see, we're able to essentially stay in second gear. In Excel and endurance, we reach top speeds of like 67 miles an hour. And if you look at the graph, our shift point for shifting into third is at around 65. But if you see right here, these are almost overlapping. So we're not really losing out on torque by staying in second gear there. And shifting takes a certain amount of time, and it's not always reliable. So if we can avoid shifting into third, that's good. That being said, for this season, we are raising the FDR. So by raising the FDR, we essentially shift our tractive effort plot to the left and up. So with gears or sprockets or anything where you've got a ratio like that, it's a trade-off between torque and speed. So the closer those gears are to the same size, the higher speed you will have, but less torque. Whereas the bigger ratio you have between the two, you'll be getting more torque but less speed. So by raising the FDR to 2.46 for this season. You can see, maybe you can't see, but it's shifted that whole graph up and to the left. So what's good is that now, so if you see 20 miles an hour on there, we're still kind of in that dip. But the differences are our torque at 20 miles an hour there is 600 pound-feet, whereas over here it was closer to like 475. So, or closer to like 500 or so. So even though we're still kind of in that dip, we're still increasing our torque by a lot. One downside is we'll have to shift into third gear for Excel, because if we were to try to stay in second here, all the way to 67, first of all, we get pretty close to red line, but we're also going to be losing out on torque at the top end there. So, yeah.
So since you're over like the traffic, it's like with this new final drive ratio, when you come out of corners at like 25, would not be worried about tire speed, I guess.
Yeah, it's a great question. So we do have traction control on this car. So like, yeah, it's not necessarily ideal to be above your tractive limit, but it's also not a problem because we have traction control. So, yeah, good question though. Anything else?
Why is the block on the zero for like 10 miles an hour?
I don't know, to be honest. It's just how it is. That's just the torque curve for the engine. It might have to do with how we do the dyno runs. Oh, it's a good question though. I should ask Shane. Anything else on these two slides here?
So you said when you raise the FDR, what happens to the torque? It increases or?
Right, so you gain torque, but you're losing speed. So your top speed for each gear is going to go down.
Okay.
Yeah, and that's true for any sort of gear chain and sprocket assembly, because it's always going to be a trade-off between speed and torque. All right, CV joints. So someone asked about that earlier. So yeah, this is where, so I think I have it all written out on the next slide. So yeah, it stands for constant velocity joint. So obviously while we're driving, the wheels are going to be moving up and down on the suspension relative to the frame of the car. But the differential is fixed to the frame. So they're not going to be in line a lot of the time. So the CV joints connect them together. And they consist of the CV housing, which is this sort of, it's called a tulip shape. So we've got one on each side of the Drexler. So I'll go back a couple slides. Yeah, so you can see we've got one coming out of each end of the Drexler. Those are also called stub shafts. And then we've got the same sort of profile as a pressed insert in the wheel hubs. So this is the uprights. So this is where the suspension comes in. And then that blue ring is a bearing. And then this whole inner part spins and the wheel connects on the other side. So that's how the power is actually transmitted from the diff to the wheels. And then you have the half shafts. So they essentially look like that. It's just a bar of steel. It's hollow. It's got splines on each end. And those mate with the tripod bearings themselves. So tripod, because there are three. They're needle roller bearings. You can kind of see the needle rollers there. These are not sealed bearings like a lot of what you guys have probably used to seeing, including like the one on there. Because inside of this joint, we pack it full of grease and then we actually cover them so that none of that grease flies out. So yeah, and that's basically the CV joint. So like you can see in this animation, they're able to have the half shaft at a different angle than the stub shaft coming out of the diff and still be able to transmit the torque. Like I was saying earlier, the higher this angle, the more stress you're putting on the whole system. So we want to try to minimize that angle when we can to avoid the bearings inside from kind of falling apart. Any other questions about CV joints? No? Cool. And yeah, that's pretty much it. So drivetrain isn't a huge system. The differential is complicated, but other than that, I think it's all pretty straightforward and understandable for most people. So, yeah. Any final questions about anything? Yeah.
When it comes to stuff like adjusting the differential, will that mainly be like theoretical, like the MATLAB lab time simulation, or will we be talking to the driver and seeing like the driver says like, hey, this is a problem? Like how much of what drivetrain does is dependent on driver feedback versus theoretical work?
Yeah, it's a good question. So like some of it, it kind of depends, I guess, is the answer. Some of it is like you look at your data that you've collected during a run. For example, if we're seeing, that that we're getting engine bog, because we can see throttle position, so we can see the position of the driver's trying to put the throttle to and see if the car is responding as fast as it should. Whereas things like tuning the diff, that's probably going to be mainly driver feedback, because at the end of the day, if the driver can't drive the car well, it doesn't matter how good of a car you have, right? Yeah. So like if you have a really experienced driver who knows how to, drive the car well, you could probably have a more aggressive locking diff. Whereas if you have a less experienced driver, it might be better to have closer to an open differential because that is a little more predictable in cornering. So yeah, good question. Anything else? Cool. All right, that's it. That's all I have. I stop recording now. Got something in the chat. Hopefully that's familiar. Jack, can you move the camera? Rip.
Oops. I guess it's worth noting to say, the powertrain systems, there's 4 of them. They all kind of work in tandem with the engine stuff.
Yeah.
So if you're like an engine guy, you can work on any 4 of them, and then we all work on engine stuff together. And they're all not that big, all 4 of them, but there's 4 different ones you can work on, and
Right.
you get very similar work, and be all work closely together.
Yeah.
So it's worth being said.
Yeah, like a competition, like powertrain is considered one system. So whereas everyone else, like suspension, they'll present their whole thing to one judge. Powertrain is going to have all 4 leads presenting a little bit of the entire system to somebody.